So these many formulae you have to memorize. Okay, these are the standard formulae of moment of inertia. And then, so standard formulae for symmetric bodies about natural axis. That's what you have to memorize. And then there are some theorems on moment of inertia. Okay, so we can use those theorems and find out moment of inertia about some other axis. So those theorems are known as the perpendicular axis theorem and the parallel axis theorem. Okay, so let's talk about the perpendicular axis theorem first. Perpendicular axis theorem. Perpendicular axis theorem. So what is this? Okay, so we'll prove it and then see. So let's suppose we have a body. I'm sorry. So let's suppose we have a body like this. This is a laminar body. So what do you mean by laminar body? It's very thin body which can lie in a plane. Okay, so it's very thin body which can lie in a plane. Okay, the thickness of this body is very small. Then for this kind of body, let's suppose you know its moment of inertia about an axis which passes through its center of mass. Okay, you know its moment of inertia about an axis which passes through its center of mass and it is perpendicular to its plane. So this axis is perpendicular to plane of this body. So let's call this axis as the z axis and the moment of inertia about this axis is suppose I suffix z. Okay, then now you can draw x and y axis which lie in the plane of this body. Okay, so suppose this is my x axis, this is my y axis, and they lie in the plane of this body. Okay, so this is x axis, this is y axis. So now if the body rotates about this z axis, how much is the moment of inertia? It is Iz. If body rotates about this x axis which lies in the plane of the body, okay, and which also passes through the center of mass, then its moment of inertia is suppose Ix. And if it rotates about this axis, okay, if the body rotates about this y axis, then its moment of inertia is suppose Iy. Then the perpendicular axis theorem says that Iz is equal to Ix plus Iy. Okay, this is the perpendicular axis theorem and it is strictly applicable to the laminar bodies only. Okay, so let's prove this theorem. So for that, let's consider a small mass of this body. Let's call this mass dm. Okay, distance of this mass from z axis is this much. Okay, let's call it r. Now we can draw perpendicular from this mass dm onto x axis and y axis. Okay, so let's draw perpendiculars. So if I draw a perpendicular over here, this is perpendicular on x axis and this is perpendicular on y axis. So this much distance is suppose x, right? And this much distance is suppose y. The distance on y axis is y. Okay, so you can see here this is mass dm. So this distance when you draw perpendicular on x axis, okay, so distance from x axis is how much? It is equal to this distance, right? So that distance is equal to y. So distance from x axis is equal to y and its distance from the y axis is equal to how much? It is equal to x, right? So its distance from y axis is this much. Okay, so it's equal to x. These are perpendicular distances. Okay, so now how much would be the moment of inertia of this mass, the small mass about z axis? So moment of inertia of this mass, let's call it dm, about the z axis will be, let's call it di suffix z. So it is equal to the mass dm multiplied by r square, where r is the distance of this mass from the z axis, right? How much would be its moment of inertia about the x axis? So tell me. So moment of inertia of dm about x axis, let's call it di suffix x, it's equal to this mass multiplied by its distance from x axis square, that is y square. And similarly we can say moment of inertia of this body, okay, the mass dm about the y axis, let's call it di suffix x, it's equal to what, dm multiplied by x square, sorry, di suffix y, it's equal to dm multiplied by x square. And then here you can say r square is equal to x square plus y square, right? Clearly r square is equal to x square plus y square. So therefore what we can say is di suffix z, moment of inertia of small mass dm about the z axis, it's equal to, okay, dm multiplied by r square, which is equal to x square plus y square according to the Pythagoras theorem. Okay, so this is equal to dm multiplied by x square, dm multiplied by x square, this is moment of inertia about y axis, plus dm multiplied by y square, this is moment of inertia about x axis. So it is di suffix y plus di suffix x. So this is diz. And now if you want moment of inertia of this complete body, laminar body, about this z axis, what will you do? You will integrate this. Okay, you will integrate this, just integrate this. Okay, so if you integrate this equation, what do you get? So if you integrate this equation, okay, then you get the moment of inertia about z axis is equal to moment of inertia about y axis plus moment of inertia about x axis, right? So you get ix or iy, let's say, plus iy. Okay, so the proof is very simple. This is the perpendicular axis theorem. Got it? Yes, no? All right. So let us see an example on this. For an example, let's consider a ring. Okay. For an example, let's consider a ring. So we know the moment of inertia of a ring about an axis which is perpendicular to its plane and passes through the center of mass. That means its center. So how much is that moment of inertia? Let's call this z axis. Okay, this is z axis. So for a ring, moment of inertia about this z axis, which is perpendicular to its plane, passes through its center of mass, it's equal to mr square. We know this. Okay, so now I want to find out its moment of inertia about a diametric axis. So I can consider two diametric axes like this. Okay, we can call them x and y. So by perpendicular axis theorem, what can we say? Iz is equal to ix plus iy, moment of inertia of the ring about the perpendicular axis which passes through the center of mass is equal to sum of the moment of inertia about two perpendicular axes. Okay, these two perpendicular axes which are perpendicular to this axis and lie in the plane of this body, okay, and also pass through the center of mass. So it's equal to, okay, ix plus iy, we can say. Now this is a diameter, right? This is diametric axis, okay, and this is also diametric axis. So by symmetry we can say moment of inertia about x-axis will be equal to moment of inertia about y-axis, right? So I can say x and y both are diametric axis, okay, both are diametric axis. So moment of inertia about x-axis is equal to moment of inertia about y-axis, and let's suppose, sorry, I said plus, it is equal to, okay, and it's equal to the moment of inertia about any diameter, you can say, okay, about any diameter. So this thing will be id, this is also id. So I suffix z, iz is equal to 2 times id, and therefore id is equal to what? id is equal to iz divided by 2, and therefore you get moment of inertia of a ring about a diametric axis is equal to, oh, what happened, it's equal to mr square divided by 2. Similarly, we can take another example. So now we talked about ring. Next, let's consider a disk. So we know the moment of inertia of a disk, sorry, so it's a very thin disk. Its moment of inertia about this axis we know. Okay, how much is this? So mi of a disk about the z axis, it's equal to what? mr square divided by 2 about an axis which is perpendicular to its plane passing through the center of mass is mr square divided by 2. Now I want moment of inertia about which axis? About a diametric axis. Okay, so we can consider this x axis, this is y axis, okay, any one of these can be called as x, anyone can be called as y, right? And similarly, okay, similar to last problem, what we can say, that ix is equal to iy, and it's equal to moment of inertia about any diameter, about any diameter, okay. So you take diameter here, moment of inertia will be same. You take diameter, okay, here, anywhere, moment of inertia about all diameters will be equal, right? So here we can say 2 times of I suffix d, because iz is equal to what? Ix plus iy, that is 2 times of I suffix d, it's equal to mr square upon 2, and therefore I suffix d for a disk is mr square divided by 4 if you take that 2 on the other side. Okay, so it is mr square divided by 4. Simple. For which kind of bodies the perpendicular axis theorem is applicable? For laminar bodies only. Okay, that means it will not be applicable for any other body like a sphere or a disk, we can say, sorry, not disk, a cylinder. Okay, so see, this is not a laminar body, okay, a sphere or a shell or a cylinder, these are not laminar bodies, so it's not applicable. The perpendicular axis theorem is not applicable for these bodies, okay. It is applicable for this kind of body, we can say, like the stab, okay. So it is a laminar body, right? It's a laminar body, it can lie in a plane. Body can have any shape, not necessarily a rectangle or a disc, okay, it can have any shape, okay. So for an example, you take a page, you cut it at any shape, you make triangle or any irregular shape, still it will be a laminar body. Got it? So perpendicular axis theorem will be applicable for laminar bodies only, not for any extended object like okay, any thick body. It will not be applicable for that. Not for a not for a cylinder, not for a sphere. Next, let's see the parallel axis theorem. This is applicable for all bodies. Okay, and so let's suppose this is some body. Okay, so let's see parallel axis theorem. So let's suppose this is some body, and you know moment of inertia of this body about this axis. Okay, about this axis which passes through some point, let's call it O. Okay, and then you have a parallel axis which passes through the center of mass of this body. So let's suppose this is the center of mass, and the perpendicular distance between these two axes is suppose h, small h. So this much is the perpendicular distance, right? And mass of this body is capital M. Then the parallel axis theorem says that IO, what is IO? Moment of inertia about this axis, which you know. So it is equal to moment of inertia about an axis which passes through the center of mass, okay, plus m into h square. Okay, so you can know any one of this. Okay, so let's suppose you know the moment of inertia of this body about an axis which passes through the center of mass. Then you can find out moment of inertia of this body about a parallel axis which passes through, let's suppose, this point. So this axis which passes through the center of mass and this axis which passes through O, they are parallel to each other. Okay, and the perpendicular distance, the distance between these two axes is h. Then the moment of inertia of this body about this axis is equal to moment of inertia about the axis passing through center of mass. But what kind of axis? So this axis is parallel to this axis. Okay, not any axis, right? So it cannot be another axis passing through center of mass like this. Okay, the two axes must be parallel, plus the mass of body multiplied by h square. What is h? The distance between two axes. So this is the parallel axis theorem. Is it clear? Okay, so now let us prove this. So let us prove this. So let's suppose we have this mass dm. Okay, so this is a small portion of this body, very small segment you can say. Okay, so its distance from this axis, perpendicular distance from this axis, okay, which passes through O, suppose r suffix O, right? Then its perpendicular distance from this axis, suppose r suffix C. Okay, so let's call this point P, and then what I will do is I will draw a perpendicular from this point P on this OC extended. Okay, so let's extend OC. Let's extend OC and let's draw a perpendicular from this point P. So it meets at any point. Let's call that point M. Okay, so this is H, OC is H, and this distance is suppose X, right? So now, so what will be moment of inertia of mass dm about this axis? Okay, let's call it O prime, O prime, and this axis is suppose C prime. Okay, so moment of inertia about this O prime axis, it is, let's call it DIO. So it's equal to mass multiplied by distance square. So dm multiplied by its perpendicular distance from this axis is r naught. Okay, dm multiplied by r naught square. Okay, and then using the Pythagoras theorem, we can say r naught square is equal to this distance square. Okay, OM square plus PM square, right? So we can write DIO is equal to DM multiplied by OM square plus PM square. This is by using Pythagoras theorem. And then OM is equal to this distance OM is equal to OC plus CM. Okay, so it is DM multiplied by OC plus CM whole square plus PM square. PM square, right? So then we can write what is OC plus CM square? It is OC square plus it is 2 times OC times CM plus CM square plus we have this PM square. Okay, and then here we can see that CM square plus PM square, it is by Pythagoras theorem again, CM square plus PM square is RC square, right? So we can say sorry, DIO is equal to OC square plus 2 times OC multiplied by CM OC multiplied by CM plus CM square plus PM square. CM square plus PM square is CP square, which is RC square. Okay, so this is RC square. So, oh, I forgot this mass, right? I forgot DM. So everything multiplied by DM we have. Okay, so we have DM multiplied by, so we have DM multiplied by this thing OC square, so which is H square. So H square plus 2 times of H multiplied by CM is X. CM is X plus then you have RC square. So what is RC square? So RC, yeah, RC square is RC square only. So RC square. Okay. Then what is DM multiplied by H square? It is DM multiplied by H square only. Then we have DM multiplied by RC square. Okay. So you have DM multiplied by H square plus DM multiplied by RC square plus 2 times, okay, DM multiplied by H multiplied by X. Right? We are just writing. These are just steps. Okay. Then, so now what is DM multiplied by RC square? So it is moment of inertia of this mass about this axis, right? It's moment of inertia of this mass about this axis. Okay, then dm multiplied by h square, so it is this mass multiplied by this distance square. Okay, so now if we integrate this, so if we integrate this over this body, what do we get? So if we integrate dio, that is moment of inertia of this mass about this axis, we'll get moment of inertia of the body about this axis. Then if we integrate this dm multiplied by rc square, okay, then we'll get moment of inertia of this body about this axis, right? So integrating, I get integration of dio is equal to integration of, now h is constant, h is distance between two axes, and it is constant. So I will take h outside. Okay, h square integration of dm. What is integration of dm? It is total mass of the body, right? Then you have plus integration of dm multiplied by rc square. What is that? So it is moment of inertia of this mass about this axis. Okay, so you can call it dic plus, again you can take 2h, okay, outside. So 2 times h you can take outside because h is a constant. It is distance between two axes. And what do you have? You have dm multiplied by x. Integration of dm multiplied by x. Okay. So then we have IO. It is moment of inertia of total body. Okay. Integration of DIO is IO, moment of inertia of total body about this axis O. Plus you have integration of dm is just total mass of the body. So m multiplied by h square plus then you have integral of dic. So it is just ic. Okay, dic is moment of inertia of this mass about this axis. Its integral over the body is moment of inertia of total body about this axis, right? So you got io is equal to ic plus mh square, but then you have this extra term also. So what will be integral of this? So I will just say for now that this integral is 0. We'll see why this is 0. Okay. So this integral will turn out to be 0, and therefore we have proved the parallel axis theorem if this is equal to 0, right? So question is, why is this integral equal to 0? So integral of dm multiplied by x over this complete body is equal to 0. We had seen this thing. All right. So see, we had seen this, that if you take moment of a mass about center of mass, because let's suppose your center of mass is given by this thing. Okay, plus m1 r1 bar plus m2 r2 bar plus so on and so forth up to mn rn bar divided by sum of all these masses, that's equal to m. And now if you take center of mass at the origin, then what will you get? Then you get that summation of mi ri bar, I goes from 1 to n, it's equal to 0. That means sum of moment of all masses about the center of mass is equal to 0. And if you have continuous body, then instead of a summation you will have an integration, right? So this is for discrete masses. If you have continuous body, instead of summation you will have integration. So this thing is 0 means that, so this is a vector, r bar is a vector. It will have three components: x component, y component, z component. Okay, so if summation of mi ri bar is equal to 0, it means that mi xi bar, summation of that, not bar. Okay, so this thing means that summation of mi xi is equal to 0, summation of mi yi is equal to 0, summation of mi zi is equal to 0, right? Identically all summations are from I goes from 1 to n. Okay, right? So all of them are 0 because a vector cannot be equal to 0 if one of the components of that vector is non-zero, right? So all components are 0. Okay, so summation of mi xi is equal to 0, summation of mi yi is equal to 0, and this thing is also equal to 0. So this is for discrete mass. If you have continuous mass, this means for a continuous mass, continuous mass distribution, you will have integral of dm multiplied by x equal to 0, integral of dm multiplied by y equal to 0, integral of dm multiplied by z is equal to 0. But all of these moments are about what? About the center of mass. Okay, so and therefore this is equal to 0. Got this? Yes, yes, no? So let's suppose you have spherical shell, spherical shell. So its moment of inertia about this axis, which passes through its center of mass. That means center only. So this moment of inertia is suppose, so this is center of mass. So IC for a spherical shell is 2 by 3 mr square. Okay, so we have to memorize this thing. Then what we can do is we can find out its moment of inertia about this axis, about a tangential axis, about a tangential axis. Let's suppose this is the tangential axis. We can find out its moment of inertia about this axis. Okay, so this point is suppose O. So our parallel axis theorem says what? IO is equal to what? IC, so moment of inertia about this axis, plus mh square, plus mh square. And what is h? What is distance between these two axes? It's equal to r. Okay, it is IC plus m into h square. Okay, sorry, it has to be square. So it is equal to 2 by 3 mr square, right? 2 by 3 mr square plus mr square. So this will be equal to what? You can say 2 by 3 mr square plus 3 by 3 mr square, which is 5 by 3 mr square. Okay, the moment of inertia of a spherical shell, of a spherical shell about axis which passes through, sorry, about a tangential axis is equal to what? 5 by 3 mr square. This is a thin rod. We know its moment of inertia about this axis which passes through its center of mass and it is perpendicular to its plane. Okay, so length of this rod is L. Then its moment of inertia about this axis is how much? IC is equal to ml square divided by 12. We had solved this. Then I want its moment of inertia about this axis which just touches one of its ends. Okay, so this end or that end. So I want its moment of inertia about this axis. So we know the parallel axis theorem says IO is equal to IC plus mh square. And how much is this distance? How much is this distance? It is L by 2, right? So h is equal to L by 2. So let's substitute IC is ml square divided by 12 plus we have m multiplied by L by 2 square. Okay, so it is ml square divided by 12 plus this will be ml square divided by 4. So ml square divided by 4. Okay, that is you can multiply and divide by 3. So 3 ml square divided by 12. So 1 ml square divided by 12 plus 3 ml square divided by 12. So you have 4 ml square upon 12. Or you can say it is, if you divide 12 by 4, you will get 1 by 3, right? So 1 by 3 ml square or ml square divided by 3. Okay, so moment of inertia of a thin rod about an axis which passes through one of its ends. So that moment of inertia is equal to what? Ml square divided by 3. So this is the formula. So this is how we can apply the parallel axis theorem. And let's talk about one more thing. It is known as radius of gyration. So what is this thing? So for an example, we have any body, we have this body of any shape, and we know moment of inertia of this body about some axis. Let's call this z axis, some axis. Okay, we know moment of inertia of this body when it rotates about this axis. Let's suppose moment of inertia is I. Okay, so now I can write this moment of inertia equal to, so let's suppose m is the mass of this body. So if I take a point of this mass, then at what distance should I keep that point such that I get the same moment of inertia as that of this body about this axis? So that distance is known as the radius of gyration of this body. Okay, so I would be equal to something. Suppose there are n number of particles within this body. So we know I is equal to summation of mi ri square. I goes from 1 to n. So this is moment of inertia of this body about this axis. So what I will do is I will replace this body. I will replace this body by a point mass. Okay, by a point mass. So at what distance should I keep that point mass? So what's the speciality of that point mass? That point mass has mass equal to this body. Okay, so mass of that point mass is equal to mass of this body. So at what distance should I keep that point mass such that this point mass will have same moment of inertia as that of this body about the same axis of rotation? So that distance is known as radius of gyration and it's denoted by k. So I is equal to what? M multiplied by k square. So that distance is suppose k. So then we can find out radius of gyration for some bodies. For an example, let's find out radius of gyration of a disk. Radius of gyration of a disk about an axis which passes through its center of mass and it is perpendicular to its plane. So this is a disk. This is an axis which passes through its center of mass and it is perpendicular to its plane. So we know that moment of inertia of this disk about this axis is equal to mr square divided by 2. We know this. So what we'll do is we'll replace this disk by a point mass. Okay, by a point mass. So let's suppose we replace this disk by this point mass. So at what distance should we keep this point mass? But what is the speciality of this point mass? It has got mass equal to this disk. So at what distance should I keep this mass such that it will have same moment of inertia as that of this disk? So that distance is known as the radius of gyration of the disk. Okay, so suppose I have to keep it at this distance. We denote it by k. Okay, so how much would be its moment of inertia? I is equal to, because it is point mass, it is, sorry, not r, it is mk square. Okay, but moment of inertia of this disk is equal to moment of inertia of this point mass when I keep this mass at distance equal to radius of gyration. Okay, so mk square is equal to mr square divided by 2. Mk square equals to mr square upon 2. So gets cancelled. K square is r square upon 2 and therefore we have k equals to r upon root 2. So the radius of gyration of a disk about its natural axis is what? It is r upon root. Very simple. Okay. So if you think about a shell, how much would be radius of gyration of a shell? Radius of gyration of a thin shell about its natural axis. So what does the natural axis mean? It means an axis which passes through its center of mass. Okay. So this is a thin shell, and we know its moment of inertia about this axis. Okay. It's equal to, I is equal to 2 by 3 mr square. We know this. Okay. So what we'll do is we'll replace this shell by a point mass. And at what distance should we keep that point mass such that it will have same moment of inertia about the same axis? So that distance is known as radius of gyration. It's denoted by k. So mass of this point mass is equal to mass of this shell. Okay. So again we can say for this point mass, I is equal to what? Mk square, and therefore mk square is equal to 2 by 3 mr square. Okay, mk square is 2 by 3 mr square. So m and m gets cancelled. So what is the value of k? K is equal to root 2 by 3 r. Okay, so what is the point of finding out this radius of gyration? Just some extra work, extra exercise? No. It gives us the distribution of mass of a body about an axis of rotation. Okay, it gives us the distribution of mass of a body about an axis of rotation. So for an example, we have, let's suppose, two kinds of wheels. One is a disc shaped wheel, okay, and one is a wheel like this. So in general, okay, whatever wheels we have for our bikes, cars, bicycles, okay, these are of this shape. So if it is a bicycle wheel, it will have spokes, right? And if it is car wheel, then there will be some kind of alloy, right? So it will be something like this. So for simplicity, let's suppose it is just a bicycle wheel. So it will have spokes, and suppose that these spokes have no mass. Okay, so these spokes are massless for simplicity. But mass of this disc, okay, mass of this disc and mass of this wheel is equal. So this m, mass of the disc and mass of the wheel is equal. So question is, which one of them will have the more moment of inertia? And let's suppose that thickness is also equal. Which one will have more moment of inertia? Because moment of inertia of a disk is mr square upon 2. Okay, question is about this axis, right? Natural axis. So it is mr square upon 2, and this is mr square. So this kind of wheel will have more moment of inertia, right? So radius of gyration of this ring will be how much? So for a disk, k is equal to r upon root 2, and for a ring, k is just equal to r. Okay, so you can say that mass of this body is distributed at distance of r from the axis of rotation. Mass of this body is distributed at distance of r by 2 from the axis of rotation. Okay, so for this body, mass is at more distance from the axis of rotation. For this body, mass is closer to the axis of rotation. If closer is the mass, less will be the moment of inertia. If farther is the mass, more will be the moment of inertia. This is the significance of radius of gyration. Got it? Yes, no? So let's see some examples. The radii of a sorry, the ratio of the radii of gyration of a circular disk to that of circular ring, each of small mass and radius around their respective axis. So when they say respective axis, it's always the natural axis. That means perpendicular axis which passes through the center of mass. So we have solved this, right? So for a disk, how much is radius of gyration? It's r by 2. For a ring, it is r. So what's the answer of this? You want this to ring, right? So it is r upon root 2 divided by r. This is radius of gyration for a disk, and this is radius of gyration for a ring. Okay, so r gets cancelled. 1 upon root 2 or 1 is to root 2 is the answer. Okay, so very simple. So let me read it again. The ratio of radii of gyration of a circular disk about tangential axis in plane of the disk. Okay, so this is a disk, right? And you want its radius of gyration about tangential axis. So this is a tangential axis. This is diametric axis. So first of all, we want to find out its moment of inertia about the tangential axis. So we had found this moment of inertia about diametric axis for a disk I suffix d for a disk is equal to mr square divided by 4. We have solved this, okay, in today's lecture itself. So about this tangential axis, how much would be its moment of inertia? So it for a disk will be what? Using parallel axis theorem, you can say it is id plus mr square, right? So how much is id? It is mr square upon 4 plus mr square. So that is 5 by 4 mr square, right? So we found moment of inertia of a disk about a tangential axis which is in plane of a disk, okay, which is in plane of a disk, okay, and circular ring of same radius and mass about tangential axis in plane of the ring. So for a circular ring, that was disk, this is ring. So for a ring, we know this, okay, id for a ring, how much is that? So about this axis, its moment of inertia is mr square. About this axis, it will be mr square divided by 2. Okay, and you want about the tangential axis. Okay, I about tangential axis, it for a ring. So it will be mr square by 2 plus mr square, because this distance is r, using parallel axis theorem. So it is 3 by 2 mr square. Then you can equate this to what? mk square and find out radius of gyration. So here it will be root of 5 by 4 r, and here it will be root of 3 by 2 r. Okay, let me add a page here. So k for disk about the tangential axis, it's equal to square root of 5 by 4 r. So we want ratio of k for disk to k for ring about the tangential axis. So this is square root of 3 by 2 r. So this r and r gets cancelled. So it is 5 by 4, and dividing by this is equal to multiplied by its reciprocal. So it is 2 by 3. So this thing, okay, 4 divided by 2 is 2. So 2 times 3 is 6. So it should be square root of 5 by 6. Okay. So option C is the answer. Alright, next one. Moment of inertia of a uniform circular disk about a diameter is I. Moment of inertia about an axis perpendicular to its plane and passing through a point on its rim will be. So again we have disk, its moment of inertia about which axis is given, about its diameter is given. So about this axis, this is given. So you want its moment of inertia about an axis perpendicular to its plane and passing through point on the rim. So not this axis, it will be axis like this. Okay, you want moment of inertia about this kind of axis, right? A point on the rim and perpendicular to its rim. So this is I. They are calling this as I. And I want I suffix z, or let's call this as I suffix t. Let's call it tangent. Okay, so t, and z axis will be like this. So I'll draw it by different color. So now Iz, how much is Iz for a disk? It is mr square upon 2, right, for a disk. Okay, moment of inertia about the perpendicular axis. How much is this? It is mr square divided by 4, right, using the perpendicular axis theorem. How much would be I suffix t? So using a parallel axis theorem, it will be Iz plus mr square. Okay, so it is mr square upon 2 plus mr square, which is 3 by 2 mr square. Okay, and how much is this I? So I is equal to mr square divided by 4. So we can substitute that. So mr square is equal to, you can say 4i. If you take that 4 on the other side, so we can substitute that here. So it is 3 by 2 multiplied by 4 times I. So that is 4 by 2 is 2. 2 times 3 is 6. So 6i is the answer. Option C. Next problem. The moment of inertia of a disk of mass m and radius r about an axis which is tangential to the circumference of disk and parallel to its diameter is. So again we have disk. We want its moment of inertia about an axis which is tangential to the circumference, okay, which is tangential and parallel to the diameter, okay, parallel to the diameter. So this is diametric axis. We want moment of inertia about a parallel axis which is tangential. This is very simple. Okay, so ID for a disk is mr square divided by 4. So this is tangential axis. IT using the parallel axis theorem will be mr square, okay, which is mh square because h is equal to r, plus mr square upon 4. Okay, so 5 by 4 mr square is the answer. Option A. The moment of inertia of a uniform disk of radius r and mass m about an axis touching the disk at its diameter and normal to the disk is. Okay, so diametric axis. Oh, what is this? The moment of inertia of a uniform circular disk. So we have uniform circular disk of radius r and mass m about an axis touching the disk at its diameter and normal to the disk is. I get this should be the rim. Okay, so you cannot have an axis which is touching the diameter, right? Touching the diameter, and it's also normal. Okay, so this should be rim, I guess. Should be this axis. right? So it will be 3 by 2 mr square. So for this axis, it is mr square upon 2. For this axis, it is how much? Mr square upon 2 plus mr square. Okay, using the parallel axis theorem. So it is 3 by 2 mr square. This is the answer. Let's see next question. A thin rod of length L and mass m is bent at its midpoint into two halves so that the angle between them is 90 degrees. Okay, so you are bending thin rod. So let's suppose you have this rod like this. You are bending it into two halves. Okay, so you have now rods like this, bending at 90 degrees. Moment of inertia of the bent rod about an axis which passing through the bending point. So you want moment of inertia of this thing about this axis and perpendicular to the plane defined by two halves. So you want moment of inertia about this axis. Okay. Yes. Now let's suppose the mass of one of these rods. So let's find moment of inertia of, let's suppose these are two rods. Okay, so moment of inertia of both of them about this point axis which is perpendicular to the rods and passing through this point. So for both of them it will be equal, right? So this is one of those two rods, you can say. So for this mass is m, length is L. For this one mass is suppose small m, which is m by 2, and length is also small l, which is L by 2. So how much would be its moment of inertia about this axis? Okay, so did we solve this? No, right? For a rod, did we solve? Yes, we solved it. It is ml square by 3, right? Moment of inertia about this axis which is passing through the end. Okay, it's ml square divided by 3 using the parallel axis theorem. Moment of inertia about this axis is ml square upon 12. About this axis, it is ml square upon 12 plus mh square. H will be L by 2, right? So it is ml square upon 3. We have solved this. Okay, so we can directly use that. So how much would be moment of inertia of this thing? Let's call it I1. It will be ml square upon 3. Okay, and you have two of those, so it will be 2 times. So total moment of inertia of this thing, let's call it I. So I will be 2 times I1, that is 2 times ml square upon 3. But what is this m? M is equal to what? For both of these, it will be equal to half of this mass. And L length is also half of this length, right? So you have 2 by 3, okay, m, which is capital M upon 2, multiplied by L is capital L upon 2 square. So this is, you will have ml square, this 2 and 2 gets cancelled, and 2 square is 4, right? 2 square is 4, so you are getting 4 3s are 12. Ml square upon 12, if my calculation is correct. So this will be the answer, option D. All right, so let us see next question. Four identical thin rods, each of mass m and length L, small l, form a square frame. Moment of inertia of this frame about an axis through center of square and perpendicular to its plane is. Okay, so you have four rods like this. So you have a frame like this. You want moment of inertia of this about an axis which passes through this point, central point, and it is perpendicular to all of them. Okay, all of these rods. I mean, it's perpendicular to the plane of the frame. How much would be moment of inertia? So we know moment of inertia of a rod about a perpendicular axis which passes through this point. It is ml square upon 12, right? For this point, it will be ml square upon 12 for this rod. Similarly, for this rod, it will be, for this point, it will be ml square upon 12, right? For all of them, it will be ml square upon 12, ml square divided by 12 about an axis which passes through their midpoint. Okay, now you want moment of inertia of this rod about this point. Okay, and two axes are perpendicular. Axis passing through this point as well as this point. They are parallel to each other. Sorry, they are parallel to each other. So you can use parallel axis theorem. So this distance is h. How much will be this distance? If this length is L, this distance will be L by 2, right? So I can say for one rod in the frame. Okay, so let's call this point O. IO is equal to IC plus MH square, which is ML square. It's capital M. Okay, so ML square upon 12 plus M multiplied by L by 2 square. So it is ml square upon 4, right? This will be ml square upon 4, or this is ml square upon 12 plus this is ml square divided by 4, or you can say 3 by 12 ml square. So this will be how much? 4 by 12 ml square, or you can say it is ml square upon 3, ml square upon 3. So this is for one of these rods. You have 4 such rods. So for 4 such rods, that is for this frame, how much would be moment of inertia about an axis which is passing through this point, and it's perpendicular to its plane? It is 4 times of this, right? So it is 4 ml square divided by 3. This is the answer, option D. So this is how we can solve questions based upon this thing, parallel and perpendicular axis theorem. All of them are simple. Okay, let's see one more. The moment of inertia of a thin uniform rod of mass m and length L about an axis passing through its midpoint and perpendicular to its length is IO. This is thin rod. So it's given that moment of inertia about this axis. It's IO. Okay, axis which is passing through its midpoint, right? Perpendicular to its length. It's IO. Its moment of inertia about an axis passing through one of its ends and perpendicular to its length is. Okay, so we had solved this, right? So you want moment of inertia about this axis. So it will be IO plus this distance is suppose h, which is L by 2. So it is IO plus mh square, right? Let's call it I only. So I will be equal to IO plus mh square. So it is IO plus m L by 2 square, which is ml square by 4. Okay, so option B is the answer. So let's see one more problem. The moment of inertia of a uniform disk is maximum about an axis perpendicular to the disk and passing through. Which point? Is it this point, this point, this point, this point? It will be this point. because IO is equal to IC, that is moment of inertia about this point, about an axis which is passing through this point, plus mh square. Okay, and if h is more, then moment of inertia will be more. So compared to this point and this point, distance of this point is more, right? So therefore, moment of inertia about this point, about an axis which is passing through this point, would be more. Very, very straightforward question.